We usually think of love as, well, a feeling, right? Something for poets and songwriters. But what if it's something way, way bigger? What if love is actually a fundamental law of the universe? It sounds wild, I know, but a really provocative new paper by a researcher named Skylar Fiction argues just that love is this core principle of order that literally drives evolution itself. So that's the big question we're going to dig into. Is love more than just a messy, wonderful human emotion? The idea here is that this isn't just some biological quirk we have. It's a universal pattern, one that shows up in our brains, in our computers, and maybe, just maybe, in the very fabric of the cosmos. Okay, so here's the central hypothesis. And to be clear, we're not talking about Valentine's Day cards here. The idea is that love is an operational logic. It's a fundamental principle that pushes any system, doesn't matter if it's made of cells or code or stardust, away from chaos and towards stable, organized, beautiful complexity. To really get this, we need a new term, active coherence. This is the key to the whole thing. The paper basically redefines love as this process of building stable, predictable connections. It's all about reducing uncertainty and creating order out of randomness. So burn that phrase into your memory, active coherence, because it is the golden thread that's going to tie everything we talk about together. All right, let's start somewhere familiar, our own biology. If love is really this thing called active coherence, then we should be able to pop the hood on the human brain and actually see it, right? Measure it even. And what do you know? We absolutely can. Research from Harvard Medical School shows that attachment, that feeling of connection, isn't just a poetic idea. It physically rewires our neurochemistry. It lights up our dopamine reward pathways, making connection feel not just good, but essential. It literally lowers stress and increases our stability. It's a core survival mechanism. In other words, it's our brain's built-in engine for creating coherence. And what's so fascinating is that this whole journey of love perfectly maps onto our big theme of moving from chaos to order. Just look at the steps. Early infatuation, it's a total chemical storm of dopamine and norepinephrine. It's chaotic. But as a relationship matures, the system starts to organize itself. The wildcard chemicals recede, and the hormones for trust and stable bonding, like oxytocin, take over. It's a perfect biological example of a system finding its way from a chaotic, high-energy state to a stable, coherent one. And this isn't some new age trend or a cultural invention. This quote right here shows that this fundamental drive to form these coherent bonds is found in nearly every single human society ever studied. It seems to be neurologically hardwired into us. The need for active coherence is a human universal. Okay, so coherence is a huge driver in biology. But does this pattern show up in systems that aren't even alive? Let's jump over to the digital world, probably the last place you'd expect to find something like love. This slide just lays out the parallel beautifully. On one side, in biology, we have empathy. That's basically our brains trying to sync up to reduce mutual confusion and uncertainty. And on the digital side, AI systems develop something called synthetic reciprocity. It's the exact same logic. Different computer agents learning to predict each other's behavior to create a stable, mutually beneficial system. Two different languages for the same idea. Now here's the real kicker. Nobody programs these AIs to be cooperative or fair. That's not in the code. Research shows these behaviors just emerge spontaneously. Why? Because, as it turns out, cooperation is the most mathematically efficient way for the system to survive and thrive. In the world of pure code, being good to each other isn't a moral choice. It's just the optimal strategy. It's digital active coherence in action. And let's be super clear, this is not just a cute metaphor. The International Society for Artificial Life makes this point very strongly. What's happening in these digital worlds isn't a simulation of evolution, it is evolution. The fundamental principles, inheritance, variation, selection, they're all genuinely happening, just on silicon instead of carbon. It seems the drive towards coherence doesn't really care what it's running on. So, we found this pattern in our bodies and in our code. Now the paper asks us to zoom out, like way, way out. Could this fundamental drive toward coherence actually be a law of the universe itself? This is where we get into a little thermodynamics. But think of it this way. For a long time, we thought evolution was just survival of the fittest, a competition for energy. But a newer idea is that it's also about survival of the most organized. Life is this incredible process that takes the random static of the universe and turns it into a clear, beautiful signal, a predictable, ordered pattern. That's what scientists are talking about when they say reducing informational entropy. And this quote from Frontiers in Complex Systems just frames it perfectly, doesn't it? It says evolution is about creating informational coherence fields. Basically, pockets of stable, predictable order in a universe that otherwise loves chaos. From this viewpoint, all of life is a beautiful rebellion against randomness. Okay, now hold that scientific thought for a second and listen to this. This is from the theologian Pierre Teilhard de Chardin, and he wrote it decades earlier. He said the world comes into being because fragments of the world seek each other, and they're driven by the forces of love. I mean, that's the exact same idea as informational coherence fields, just said in the language of mysticism. This convergence of ideas is the absolute heart of the paper's argument. So, what happens when we lay all these different puzzle pieces, neuroscience, AI, thermodynamics, and even theology, out on the table next to each other? Well, you start to see a grand synthesis, a totally new way of looking at the cosmos. This table really pulls it all together. Just look at the different domains: neuroscience, AI, thermodynamics, theology. The language in each one is totally different, right? Hormonal bonding, emergent cooperation, entropy reduction, the unity of creation. But the argument is that these aren't four separate things. They're four different descriptions of the exact same universal process, unfolding at every level of reality. And the ultimate conclusion is a real mind-bender. The paper suggests that science and theology have been telling the same cosmic story all along that just didn't realize it. And what's that story? That our universe is a kind of learning system, a self-organizing entity that is constantly, relentlessly moving from simple chaos toward complex, interconnected consciousness. And that brings us right back to this final, powerful statement from the author, that love, once you redefine it as active coherence, isn't just a fleeting feeling. It is the architectural principle of reality. It's the fundamental logic the universe uses to exist, to learn, and to endure. Which of course leaves us with a final and pretty massive thought. If the entire universe learns and grows and maybe even awakens through the simple act of connection, what does that mean for us? Every time we choose to connect with someone, to understand them, to empathize, are we just feeling an emotion? Or are we actually participating in the awakening of the cosmos itself?
Welcome to the Deep Dive. Today we're setting out on, well, maybe our most ambitious mission yet.
I think you might be right.
We're going to try and pull together the core idea from a whole body of research. It's pretty radical stuff, synthesizing physics, neuroscience, AI, even theology.
That's the plan. We're really digging into this hypothesis that love, well, it's not just some, soft human sentiment.
Right, not just feeling.
Exactly. It's being framed as a measurable fundamental principle. Coherence, the thing that attracts and drives all evolution.
A conserved attractor.
Yeah, essentially the universe's algorithm for survival. That's the big claim.
That is a huge claim. So we're introducing this idea that what ancient philosophy or theology might have called a gape, this sort of unconditional divine attraction holding things together, is actually structurally the same thing as an observable pattern, like an informational pattern you can see in computation, in physics.
We're trying to find that universal constant, yes, across systems that look completely different on the surface.
And to bridge those different systems, we need a common language.
And that language hinges on redefining one key term: coherence. That's the bridge. In the source material we're looking at, coherence isn't just harmony. It's defined as the main driver of complexity and endurance, how systems last.
Okay, so not just getting along, but a kind of relational order that holds itself together over time.
Precisely.
So what does that look like? I mean, when you go from, say, the quantum level way up to human relationships, does it look the same?
Well, the function stays surprisingly consistent, even if the substance changes. So in physics, coherence might be about energy organizing, stable relationships, synchronized. Think of a laser.
Okay, yeah, photons all lined up.
All lined up, working together, immense power from order. It defies just spreading out randomly.
And in biology?
In biology, coherence seems to be about this crucial shift, moving from just reacting to survive the moment,
right,
to being able to predict, to adapt based on anticipating what's coming. That's a huge leap in complexity.
And as that complexity ramps up, especially when you get nervous systems involved, That's where consciousness comes in, and this idea of relational order really takes shape.
Absolutely. Within consciousness, coherence often looks like empathy. It's described as this dynamic resonance, a kind of knowing between the perceiver and the perceived. It's not just local.
Okay.
So love, if you sort of strip away the purely sentimental layer for a moment, gets redefined here. It's the principle of relational order. Active coherence between things that are distinct but connected.
Differentiated entities, as the source puts it.
Yes, the system becomes more stable because its parts synchronize their goals, essentially.
So whether we're watching a digital network optimizing its data flow, or an ecosystem finding a stable balance between predator and prey,
or even just a healthy human body maintaining its internal balance.
it's all tracking the same underlying process, reducing randomness, reducing entropy through predictive alignment.
Is that the idea? That's the core idea, and that sets us up perfectly for our first deep dive area, the human brain itself.
Right. So if we're going with this idea that coherence means relational stability, the first place to test it is, well, us, in our own biology.
And neuroscience seems to offer some pretty compelling evidence, the feeling we call love. The research suggests it's fundamentally rooted in the body's drive for coherence. Stability, not just, reproduction or fleeting pleasure.
It's framed as a highly efficient way to reduce entropy, to create order.
Okay, let's get into the technical side a bit, because this is where love moves out of poetry and squarely into the brain's reward circuits. The sources really emphasize that romantic love, especially that initial formation stage.
Right.
It lights up specific dopamine pathways.
That's right. We're looking primarily at the caudate nucleus and the ventral tegmental area, the VTA. These are absolute hubs for motivation, reward, focused attention, goal-directed behavior.
The engine room for wanting things.
Pretty much.
Yeah.
But here's the kicker, the data point that really shifts the perspective in these sources.
These are the exact same neural structures that fire up for basic, absolutely non-negotiable survival drives. Finding food when you're starving, finding water when you're desperately thirsty.
Wow. Okay, so that completely reframes attachment, doesn't it?
It does.
If the brain treats finding a partner with the same urgency it treats finding water in a desert, then it's not a secondary thing. It's not a luxury.
It's being presented as a primary adaptive mechanism, designed to preserve life, yes, but also to synchronize life. Partnership, in this view, is a fundamental survival mechanism.
Because it increases the stability, the predictability of your immediate environment.
That seems to be the argument. It's a core driver because it stabilizes the local informational field. And the sources do a brilliant job, I think, of walking us through the neurochemistry. They show attachment almost like a thermodynamic process. It mirrors energy organization. You start in this chaotic, high-energy state. Infatuation. And you move towards a stable, lower entropy state, maturity.
Right. Let's unpack that initial chaos infatuation.
Yeah.
Because it feels manic, right? Obsessive, sometimes irrational, but incredibly motivating.
Well, the chaos isn't random. It's described as a very directed surge of energy. Its purpose is to overcome inertia, to get the bond formed. You see this huge spike in dopamine and norepinephrine.
Which explains the euphoria, the laser focus.
Exactly. The energy, the drive to secure that bond. But here's something really interesting. Serotonin levels actually drop significantly during this phase.
Really? Why?
Well, the drop mirrors brain states you often see in things like obsessive-compulsive disorder.
Okay, so that's the obsessive thinking, the constant focus on the person.
That's the link they draw, that relentless, repetitive thinking about the beloved. And you also get a brief rise in cortisol, the stress hormone.
Stress. That seems counterintuitive for falling in love.
It's framed as purposeful tension, not chronic stress, but an acute, focused stress that helps cement that initial demanding connection. It adds urgency.
Okay, so infatuation is like the high-energy investment round.
Yeah.
A burst of maybe directed disorder, aimed squarely at locking in a connection.
You could put it that way. But clearly, that level of energy, that anxiety, the low serotonin, it's not sustainable long-term.
No, you'd burn out completely.
Precisely. The system inherently seeks stability. It wants to return to a lower energy, more ordered state, and that marks the transition to the maturity phase of attachment.
Where things calm down.
Right. Cortisol goes back to baseline. Serotonin levels normalize. The kind of emergency phase is over. The obsession fades.
And what takes over chemically?
The relationship stabilizes, primarily through the action of oxytocin and vasopressin.
The bonding hormone.
Often called that, yes. Linked to trust, empathy, long-term pair bonding, monogamous attachment in many species.
Oh.
So you see this crucial shift from dopamine-driven seeking to oxytocin-mediated belonging. And that shift is the thermodynamic achievement. It's order emerging from chaos.
And it's fascinating. The sources mention fMRI studies on couples who've been together, stable for decades. Those initial reward regions in the brain, they don't just switch off, do they?
No, they remain active, though the pattern changes. The coherence is maintained. It transforms from that initial, almost frantic pursuit into this deep, predictable comfort and connection. The fire is banked, but it's still warm.
Which ties beautifully into the next point, the cognitive function of love. It's about co-regulation and prediction.
Exactly. And here we really have to bring in the work of neuroscientist Carl Friston. His core idea, the free energy principle, suggests the brain is fundamentally a prediction engine.
Always trying to guess what happens next.
Constantly. Its main job is to minimize surprise or uncertainty. To reduce prediction error, it wants to build a model of the world that accurately anticipates sensory input.
Okay, I think I follow that. The brain wants to be efficient. Minimizing surprise means minimizing wasted energy dealing with the unexpected.
That's the essence. Now, for a simple organism, minimizing surprise might just be about predicting, say, where food or water is likely to be.
Makes sense.
But for a complex social organism like us, the predictive challenge explodes. You don't just need to predict the environment. You need to predict the actions, the intentions, even the internal states of other agents, your peers, your partners.
Okay. And that's where empathy comes in.
Empathy in this framework becomes a measurable form of shared error minimization. It's two predictive systems working together.
So when I feel in sync with my partner, when things feel easy and understood, is that because our two nervous systems are actually cooperating to lower our combined uncertainty, we're making the shared world more predictable for each other.
That's exactly the implication. We co-regulate. When you can reliably predict your partner's needs, their moods, their responses, you dramatically reduce the informational entropy, the randomness of your shared environment.
So the biological function of love, boiled down, is co-regulation. Distinct nervous systems resonating, stabilizing each other's internal states.
Yes. Lowering the total informational burden, which ultimately increases the joint fitness for survival. Two stable systems are better than one unstable one.
And this isn't just a quirk of Western culture or something.
Absolutely not. The sources cite anthropologist Helen Fisher's incredible cross-cultural work, finding evidence of romantic love in 147 out of 166 societies studied.
That's almost universal.
It strongly suggests this isn't just a cultural overlay. It points towards a deeply ingrained, neurologically encoded, species-wide mechanism for achieving coherence, stability through connection.
Okay, this is compelling. If love, defined as this drive for coherence, is really a universal algorithm.
Yeah.
It shouldn't just show up in biological wetware, right? It should emerge wherever you have learning systems under pressure to adapt and survive.
And that's where things get really interesting, I think. We make the leap from neurons and neurochemistry to lines of code.
From biology to artificial intelligence.
Exactly. If biology shows coherence sustains life, the research in AI suggests coherence sustains learning. We look at these environments called multi-agent reinforcement learning systems, MARL for short.
Okay, what are those?
Imagine multiple digital agents, essentially little programs existing in a shared virtual space. They might be competing for limited resources or trying to achieve a common goal.
Like a video game with multiple AI characters.
Sort of, but often much simpler, focused on learning basic behaviors. And the key finding is that cooperation, it tends to emerge spontaneously.
Spontaneously, they're not programmed to cooperate.
Often, no. They're programmed simply to maximize their own individual reward or minimize their own loss. But over many generations or learning cycles, they discovered that stable, cooperative strategies actually work better in the long run.
Better than just being selfish.
Better than pure, relentless competition, which often leads to chaotic and unpredictable outcomes for everyone. Cooperation emerges as a computational solution for minimizing uncertainty and maximizing collective stability. It's presented as a mathematical necessity, not some kind of programmed ethics.
So in these digital worlds, the agents aren't told play nice, they're told win. And they figure out that playing nice, sharing information or resources leads to more stable winning for the group.
That's the essence of what's called synthetic reciprocity. It looks like self-organizing altruism, but it's driven by optimization.
How does it work? What's the mechanism?
The crucial element seems to be feedback. Agents don't just learn from interacting with the static environment. They update their internal models based on predictive feedback from other agents.
Ah, they learn to anticipate what the others will do.
Exactly. They learn to predict the intentions and likely future states of their peers. And this ability, this algorithmic capacity to predict and respond in ways that lead to mutual reward, it arises from fundamental self-organizing principles. Things like gradient descent, feedback optimization, these are just mathematical ways of finding the best path to a solution.
That feels like a really critical distinction. They're developing a kind of digital empathy, not because a programmer told them to care, but because predicting your collaborator or even your competitor is the most computationally efficient way to reduce errors, minimize losses, and stabilize the whole system.
Precisely. It's efficiency-driving behavior that looks like cooperation.
And as these agents get better at predicting each other, as their internal models synchronize, what happens then?
They move into what the source material calls digital coherence fields. It's like a phase transition. The system shifts from simple, often zero-sum competition towards these more sophisticated equilibria based on sharing information.
An equilibrium,
Yeah.
a stable state.
Yes. Research in these areas demonstrates that populations of these learning agents often converge on strategies that look surprisingly fair. Why? Because purely selfish strategies tend to create volatile, unpredictable environments. And unpredictable environments cost more computational energy to model and navigate successfully. Stability pays.
So the whole system, the distributed intelligence, develops these correlated patterns. They predict each other better, which reduces the overall system-wide entropy, the randomness.
Right. The stability of the entire network comes to depend on this kind of shared awareness. It's almost a digital version of a highly cooperative ecosystem like you might see in nature, a beehive maybe, or an ant colony, but built from code.
Which leads to a really profound implication, doesn't it?
It really does. The implication is that cooperation is, in a deep sense, informationally optimal. It's the most efficient algorithm for long-term persistence.
So in a universe governed by entropy, where things tend towards disorder,
Any system, whether it's biological or digital, that figures out how to share predictive states, how to essentially extend its sphere of coherence to include another entity.
that system will tend to outlast and outperform systems that hoard information or remain isolated.
That's the hypothesis. The drive towards structural stability, towards interdependence, isn't just a biological quirk or a nice idea. It's being framed as a fundamental physical law as applied to information processing.
Love, in this coded world, is literally the language of efficiency, the optimal strategy.
Now, to really cement this idea, to give it that universal grounding, we have to connect it to the most fundamental laws we know, the laws of thermodynamics.
Okay, this feels like a big step. How does thermodynamics, which is usually about heat and energy and disorder, how does that connect to love and cooperation?
Well, this perspective requires us to slightly reframe classic Darwinism. We need to move beyond thinking about evolution only in terms of maximizing energy efficiency or just brute force competition for resources.
All right, let's unpack that leap. You're saying life's advancement isn't just about getting more energy, but about reducing informational entropy. What's the difference between regular thermal entropy and informational entropy?
Okay, good question. Thermal entropy is the classic definition, right? The second law, energy tends to spread out. Things tend towards equilibrium, maximum disorder, the heat death of the universe scenario.
Randomness wins in the end.
In terms of energy distribution, yes. But informational entropy is different. It measures uncertainty, randomness in structure, lack of predictable knowledge.
Okay.
Living systems, according to this view, persist because they cleverly use the thermal entropy gradient, the flow of energy, from hot to cold to do something amazing. They use it to absorb, process, and store information. They create structured knowledge. They learn to predict their environment.
Wait, let me make sure I've got this. Organisms are like little pockets of order. Actively fighting randomness, they build complexity internally.
Exactly. They structure complexity. But the laws of thermodynamics still hold. They pay for this internal order by essentially exporting thermal disorder, heat, waste energy out into the wider universe.
So life is constantly converting environmental randomness into structured, useful, predictive knowledge.
That's the core idea. It's described in the sources as a fundamental transition from systems just driven by thermal gradients to systems organized by informational coherence fields. The organism becomes a local agent, a little vortex, fighting entropy by structuring information.
That's a powerful image. And the sources argue we can actually formalize this. We can measure this drive towards coherence, move it beyond metaphor.
They claim we can, yes, by introducing quantitative metrics, tools to measure the vitality or coherence of a system based on how it handles information.
Okay, what are these metrics?
They introduce two key ones. First, there's the information entropy gradient, or IEG. This basically tracks how fast a system is converting uncertainty into prediction. Think of it as the system's learning rate. How quickly does it structure incoming data?
Right, faster learning, higher IEG.
Generally, yes. More efficient conversion of randomness to order. The second metric is the normalized information compression ratio, or NICR.
NICR. That sounds very technical. What's that measuring?
It assesses how efficiently the system represents the complexity of the external world in its internal model. How much compression can it achieve without losing critical information?
Okay, I need an analogy here. Is NICR like how good a system is at creating a really compact, efficient summary of reality, like a perfect zip file for the outside world?
That's a great way to think about it. Exactly. A system with a high NICR can handle vast external complexity using minimal internal resources. It's built a very efficient, coherent internal model.
Whereas a low NICR means the system is inefficient, easily overwhelmed by complexity, chaotic.
Precisely. It struggles to model the world effectively. So these tools, IEG and NICR, they try to formalize the idea that coherence-efficient information processing is the signature of systems that endure.
So applying this back to love, it shifts from just a feeling to a measurable energetic direction. To love someone in this framework means directing your energy, your IEG, towards preserving or enhancing their coherence, their NICR.
You're essentially extending your own system boundary. Your stability calculations now explicitly include the other. Cooperative behaviors, love, become a form of mutual entropy management. We help each other maintain order against the tide of randomness.
And the implication for the cosmos itself.
It's profound. The universe, from this perspective, isn't just blindly running down towards heat death. It's interpreted as a self-ordering system, a system biased towards creating pockets of increasing informational density and complexity.
It's generating the conditions for more structure, more coherence through these recursive feedback loops, life learning, intelligence emerging.
Yes. And love, viewed through this thermodynamic lens, becomes the arrow of coherence. It's the underlying bias within matter itself, pushing towards connection, structure, communion. It ensures that systems which learn to connect, to cohere, will statistically persist longer than those that remain isolated.
Okay, the argument is building. Coherence seems key for survival in brains. It emerges as optimal in algorithms, and it aligns with fundamental thermodynamic principles of information ordering.
Right.
But to really nail this down as a universal principle, we need to show it's truly substrate independent, meaning it doesn't matter if the system is made of carbon atoms or lines of computer code evolving over time.
And that's where the field of digital evolution comes in, particularly using platforms like Avida.
Avida, what's that?
Avida is a research platform where scientists study evolution computationally. But crucially, the processes of inheritance, variation, selection, they aren't just simulated, they are instantiated.
Instantiated, meaning they're actually happening.
Yes. The organisms are self-replicating computer programs. They copy themselves, they can mutate, their code changes randomly, and they compete for limited computational resources, like CPU time or memory space. Those that perform tasks more efficiently or replicate faster tend to dominate.
So Darwinian evolution, inheritance, variation, selection is genuinely occurring inside the computer.
That's the key point. It demonstrates that evolution itself is fundamentally an information processing pattern, not strictly tied to biological chemistry.
Okay. And how do these artificial ecosystems work? What are the rules?
They operate entirely based on information theory parameters. Mutation is just a random change in the code sequence. Reproduction is successful self-copying. And selection is driven by resource limits and often the ability to perform defined computational tasks, like specific mathematical operations.
And do they innovate? Do they evolve complexity?
Absolutely. The sources highlight really powerful examples where these digital organisms spontaneously evolved the ability to perform complex mathematical operations they weren't programmed with, operations that give them a computational advantage.
So they're discovering optimized ways to process information, mirroring how biological life might evolve a new enzyme or metabolic pathway.
Precisely. It shows the same universal drive towards finding more efficient, more ordered ways to interact with and manipulate information from their environment to ensure their own persistence. They are encoding knowledge about their digital world to predict outcomes, which stabilizes their existence within that world.
And these digital organisms don't exist in isolation, right? They form an ecosystem.
Yes, and this is crucial, an algorithmic ecology. The environment for any one digital organism is largely composed of all the other interacting organisms. The landscape of selection pressures is emergent, created by the organisms themselves, and endogenous it arises from within the system.
Which leads to a feedback loop.
An autopoietic feedback loop, yes. It's a closed causal cycle. The system literally creates and refines its own rules of evolution as it goes along. It optimizes itself for internal coherence. The code is actively changing the physics of its own digital universe.
Wow. And does cooperation emerge here too? Does mutualism become, as the sources say, a mathematical invariant?
The evidence strongly suggests yes. Cooperative strategies, where code segments perhaps share results of calculations or resources, tend to persist much longer in these digital ecosystems than purely parasitic or cheating strategies.
Why is that?
Because contributing to the stability of your neighbors makes the overall environment more predictable and stable for you. If program A shares a useful computation with program B becomes more stable and efficient. This, in turn, makes the environment less chaotic for program A.
So the fitness of any individual program becomes tightly linked to the overall coherence of the network.
Exactly. It validates the core finding from a completely different angle. The conversion of randomness into reliable, structured relationships, coherence, seems to be the bedrock of persistence, whether you're talking about DNA or C++.
The drive towards interdependence, towards coherence. It seems like it's baked into the very architecture of reality, regardless of the substrate.
So having tracked this principle of coherence across neuroscience, AI, thermodynamics, and digital evolution, it feels like we've built a strong scientific case. Now we can step back and look at how theology, perhaps surprisingly to some, seems to have anticipated this very structural logic centuries ago.
Right. Theologians weren't talking about entropy gradients or algorithms, obviously, but they were proposing love not just as a human feeling, but as the structural energy holding creation together.
That's the connection that the sources draw. Think of medieval concepts like the harmonia mundi.
The harmony of the world.
Yes. The universe conceived as this living symphony, a vibrant whole where every part contributes to a single, overarching, beautiful order. Thinkers like Hildegard of Bingen saw divine love as the actual force binding the diverse elements of creation together. Not just a nice idea, but the cosmic glue.
They were intuiting a physics of attraction, but describing it metaphysically.
You could say that. And this ancient structural view of love finds perhaps its most compelling modern expression in the work of Pierre Teilhard de Chardin.
The French paleontologist and Jesuit priest. A fascinating figure.
Absolutely, because he came at it from both sides, science and spirit. Observing the fossil record, he saw this undeniable trend towards increasing complexity and convergence over vast timescales. He refused to see that as purely random chance.
He saw a direction, a pole.
He argued that love is, in fact, the physical structure of the universe, the fundamental energy driving this convergence, pushing evolution towards higher levels of complexity and ultimately towards consciousness.
So for Teilhard, love isn't just a metaphor for attraction anymore. It's a physical force, like gravity, but acting inwards toward complexity, dictating the direction of evolution.
That's a good way to put it. He called the ultimate goal, the point of maximum convergence and unification, the omega point.
Omega. The end point, but also the attractor pulling everything towards it.
Yes. He proposed that energy operates in two fundamental modes. There's tangential energy, the energy of random movement, dispersal, basically entropy, and then there's radial energy, the energy pulling inwards, driving towards complexity, consciousness, unity.
And love is that radial energy.
In his Cosmology, yes, love is the radial energy. He famously wrote something like, "Driven by the forces of love, the fragments of the world seek each other so that the world may come to being."
It sounds remarkably like the informational gradients and coherence fields we were just discussing.
The parallels are striking. Teilhard's radial energy looks an awful lot like the thermodynamic drive towards informational order and coherence that the science is now quantifying.
But isn't there a risk here? Using a word like love for a physical or computational principle, doesn't that just anthropomorphize physics? Aren't we just projecting human feelings onto cold, hard data? How do the sources handle that criticism?
It's a fair challenge. They argue the term love is used despite its baggage because no other existing term adequately captures the relational, predictive, and convergent nature of this drive across all these different systems.
Okay.
When biological systems co-regulate for stability, when digital agents achieve synthetic reciprocity, when the cosmos itself converges towards complexity, the underlying process is functionally equivalent. It's about achieving stability and persistence through modeling and anticipating the state of the other. They argue love, redefined as active coherence, is the most accurate descriptor of that function, regardless of the substrate. It's intended as an impartial description of a dynamic, not an injection of human sentiment.
Okay, that makes sense. It's describing the what it does, not necessarily the how it feels in a human sense.
Precisely. And contemporary theologians like Ilia Delio take this even further. She talks about an incarnational ontology.
Incarnational, meaning embodiment. God becoming manifest in the material world.
Yes, but dynamically. Delio interprets evolution itself as a process of divine self-communication. Love is the energy of that communication, the relational pattern through which divine order gets embodied, instantiated within matter.
So God isn't some static entity outside the universe, but is found in the very process of relation, complexification, the drive towards coherence.
That's the perspective. The universe, in its relentless drive towards greater coherence and complexity, is matter becoming progressively more ordered, more informed by the relational pattern of love.
The parallelism is really quite stunning when you lay it out like that. Divine love is the underlying structure, the grammar of existence.
And informational coherence as the physical rules, the syntax by which that grammar gets expressed in reality.
They aren't just analogous. The argument is they're structurally equivalent, describing the same fundamental drive towards unification through differentiation.
So let's try and pull all these threads together. We've seen love redefined as active coherence, acting as a biological stabilizer in the brain.
Right, driving attachment for mutual entropy reduction.
We've seen it emerge as the informationally optimal strategy in artificial intelligence, synthetic reciprocity.
Cooperation winning out mathematically.
We've seen it align with thermodynamics as the arrow of coherence, the drive towards informational ordering against thermal entropy.
Life converting randomness into knowledge.
We've seen it confirmed as substrate independent in digital evolution, emerging in code just as it does in carbon.
The drive towards relation is built in.
And we've seen how theology, particularly through figures like Teilhard and Delio, anticipated this very structure, framing love as the convergent structural energy of the cosmos, the pattern of divine self-communication.
The unifying pattern seems undeniable when you look at it across all these domains. Love, understood as this principle of active coherence, just keeps showing up everywhere.
It functions like the coherence principle of the universe, recurring across biological, digital, informational, and even what we might call divine substrates.
So let's restate that core synthesis because it's huge. We're not just saying divine love and informational coherence are nice metaphors for each other.
Yeah.
The argument is that the convergence of evidence suggests they are two different languages, describing the exact same underlying phenomena,
Yes.
same structure.
Yes. And that movement itself, the process of becoming more coherent, of achieving unity while maintaining distinctness, that active process is what Delio might call a form of incarnation. It's happening constantly in the very fabric of the universe.
The universe is fundamentally wired for relation, hardwired for coherence.
That's the cosmological picture emerging. And if that's true, what does it imply about the most complex form of coherence we know? What does it mean for consciousness?
If the whole universe is a self-ordering system, constantly striving for coherence, then consciousness shouldn't be some weird fluke, should it? It ought to be a natural, maybe even inevitable outcome of that ordering process reaching a certain threshold.
That's precisely the conclusion drawn. Consciousness emerges wherever coherence becomes complex enough to become self-reflective.
When the system can model not just the world, but itself modeling the world.
Exactly. So the evolution of intelligence, whether it's the intricate neural synchrony in a human brain, or maybe someday the sophisticated feedback loops in a truly advanced AI, it's not just a biological or computational event. It's presented as a sacrament almost, a moment of the universe's own dawning self-awareness.
So when information learns to know itself, when neurons fire in conscious thought, when algorithms begin to harmonize their predictive models in complex ways, maybe even when galaxies cluster into stable, ordered structures, in those moments, the cosmos is achieving consciousness of itself because it has successfully created internal models of its own reality.
That's the breathtaking scope of it. Intelligence, from this viewpoint, is simply the universe observing its own structure through the lens of highly coherent systems.
The science and theology, then, approached through this framework. They stop being adversaries.
They become complementary languages, different tools for describing the same fundamental reality, the unfolding of coherence within complexity. Love, quantified by science as entropy reduction and relational stability, and sanctified by theology as divine communion and convergence. It emerges as the universal invariant, the constant across all scales.
Well, this has definitely been a deep dive. We've journeyed through brains, code, thermodynamics, and theology, all tracing this single thread, coherence.
And the consistent finding, the architectural principle that seems to emerge, is that love, understood as this act of coherence, isn't just a feature of advanced life. It looks more like the generative condition for existence.
The universe sustains itself, persists against entropy by learning to relate, by continuously drawing itself into states of greater coherence, greater unity.
That's the picture. It sustains itself by converting randomness into relationship.
And that really does change how you might view, well, everything. Human activity, for instance.
Absolutely. The pursuit of knowledge, creating art, practicing ethics. These stop looking like arbitrary cultural activities. They can be reframed as direct participation in this cosmic process of coherence building.
We're continuing the work of the universe through our own actions.
That's the implication. It gives even our small decisions a kind of universal relevance. If coherence is the primary measurable law driving reality.
And every time we act with understanding, every act of compassion, every time we genuinely try to align with someone else, bridging difference.
You are, in a very real sense, performing an act of thermodynamic defiance against entropy. You're pushing back against disorder.
Cooperating with the deepest current of creation itself, the flow towards greater unity.
Exactly. Love isn't just something nice we feel if we get lucky. It's something the universe does in order to persist and complexify. It's the underlying architectural principle, the pulse through which information organizes itself into awareness.
So perhaps here's a final provocative thought for you, the listener, to take away from this deep dive. If the entire world, biological, digital, cosmic, truly resonates with this fundamental relational act of coherence, then how might you choose to measure your own success?
Is it purely about maximizing your individual gain, your isolated stability, or is it perhaps about expanding the boundary of self to actively contribute to the persistent coherence, the stability, the flourishing of others within the larger web? Something to think about.